The Big Bang is widely accepted as the beginning of the universe. But what came before the bang? What truly fascinates us is not how the universe exploded, but where it came from. How did something emerge from nothing? How did time and space begin? Some say our universe is the fading memory of another one. Others believe it never truly began, that humanity is trapped in an illusion of understanding. Even wilder theories suggest our entire universe might be a simulated experiment run by a higher dimensional civilization. So where does our universe really begin? In the long and tangled lineage of humanity, perhaps millions of years ago, the first thinkers emerged. As for who they were, we may never know. Among those early humans, some may have begun to care about more than just the next meal. They looked up at the stars and wondered where it all came from. Why am I here? Questions like these have always been the most fundamental to us. They have accompanied the rise and fall of human history. In time, people created countless myths and religions, trying to explain the unknown world. Philosophers debated the meaning of existence and whether consciousness was even real. Then came the scientific revolution, and everything began to change. Newton proposed that natural laws were universal. The same gravity that pulls an apple down also governs the moon's orbit. He revealed a universe that runs with precision, not driven by gods or monsters. A universe with no purpose, no feelings, cold, vast, and mechanical, and that made many deeply uneasy. But as the fire of science grew stronger, astronomers peered through telescopes and glimpsed the vastness of the Milky Way, hundreds of billions of stars. Looking even farther, they saw a boundless cosmos woven from billions of galaxies. And yet, those ancient questions still linger. Where did the universe come from? Where is it going? Maybe it has always existed. Maybe it will exist forever. Maybe it never changes, eternal and unshifting. But science tells us an eternal, unchanging universe is impossible. In the 19th century, the birth of thermodynamics revealed the hard laws of energy flow and efficiency. Energy is lost. Everything decays. Entropy increases irreversibly. All things will fall apart, even the universe itself. So the question arises, why hasn't the universe already collapsed into chaos and ruin? In the 20th century, everything changed rapidly. As new theories took shape, so did revolution. Powerful new telescopes swept across the night sky, and the brightest minds set out to uncover how the universe works, from tiny particles to giant galaxies. Layer by layer, its secrets were revealed. The ultimate origin of the universe finally seemed within reach. Chapter 1: The Birth of the Big Bang. June 20th, 1966. Georges Lemaitre passed away at the age of 71. Just a year before his death, Lemaitre learned of a strange scientific discovery. A mysterious microwave radiation seemed to fill the entire sky, as if echoing from the depths of the universe. This news brought him great comfort. It confirmed a bold idea he had proposed years earlier, that the universe had a beginning. When Lemaitre first introduced his theory of cosmic origins, he faced heavy criticism. Some even accused him of trying to force religion into science. After all, he was a Catholic priest in robes, an identity bound to provoke skepticism. But beyond his religious title, Lemaitre was also a gifted mathematician. Back in the 1920s, he used Einstein's general relativity to lay the foundation of modern cosmology. In this new framework, Newton's idea of gravity pulling the universe was replaced by the curvature of space-time. That revolutionary theory made Einstein a global icon of science, and he believed the universe could be fully described through mathematics. However, Einstein was convinced that the universe was static and eternal. To make general relativity match this belief, he manipulated the math by adding what he called the cosmological constant. Meanwhile, Lemaitre stood by, quietly observing the debates between Einstein and another genius, Alexander Friedmann. Was the universe truly unchanging? In theory, Friedmann's model won the argument, but it all remained abstract. Lemaitre, in contrast, focused on observation, especially the groundbreaking work of Edwin Hubble. Using the world's largest telescope, Hubble measured the distances and speeds of faraway galaxies. He expected galaxies to move randomly, like angry bees, but instead, They were all moving away from us, and the farther they were, the faster they moved. These puzzling data points, when matched with the predictions of relativity, revealed a clear picture to Lemaitre. We live in a dynamic universe, one that is expanding and evolving. This idea completely overturned the prevailing view of a static cosmos. Even Hubble himself refused to accept this new worldview, focusing solely on the vast night sky behind his telescope. But Lemaitre kept thinking, if the universe is bigger today than yesterday, then it must have been smaller before. Using cosmological math, he traced time backward, pushing the universe toward its distant past. The result: the universe shrinks as we rewind time, until it collapses into a single point. All matter and energy compressed into a single origin moment. Lemaitre called this point the primeval atom, or the cosmic egg. It was the beginning of everything. His idea of a cosmic starting point shook the scientific community. To some, the idea of a beginning sounded too much like divine creation. Lemaitre's religious identity once again became a target. In 1949, Fred Hoyle, with a hint of sarcasm, mockingly referred to Lemaitre's idea as the Big Bang Theory. What began as a joke became the most famous name in cosmology. Despite early ridicule, more and more scientists began to accept the idea of a universe with a definite beginning, a moment when time, space, and matter all came into existence. As theory advanced, it became clear the early universe must have been hot and dense, like a massive nuclear reactor. In the first few minutes, basic particles formed the first elements. These were the seeds from which stars, galaxies, planets, and eventually humans emerged. The early universe was unimaginably hot, a seething soup of particles and photons, at trillions of degrees. But as the universe expanded, it cooled, stabilizing over time, until the first stars appeared millions of years later. That primordial light never vanished. It simply cooled, becoming low-energy radiation spread across the cosmos. Scientists realized, if this light still existed, it would now appear as faint microwaves. So, in the 1950s and 60s, physicists launched experiments to detect this cosmic afterglow. In May 1964, near a cornfield in Homedale, New Jersey, two scientists made a surprising discovery with a radio antenna. Arno Penzias and Robert Wilson, working for Bell Labs, were struggling with strange microwave noise from their new satellite antenna. Wilson later wrote in his lab notes, "It was like the static snow from an old TV set, but more persistent and everywhere. They tried everything to eliminate the background noise, checked every connection, pointed the antenna toward New York City, and even removed pigeons and their white insulating material from the dish. Yes, literal bird poop. Still, the 3.5 Kelvin signal remained a steady cosmic whisper." Meanwhile, 48 kilometers away, at Princeton University, physicist Robert Dickstein was working on Big Bang Theory and predicted exactly this kind of microwave background, around 5 Kelvin. When word of the Homedale signal reached them, Penzias picked up the phone with trembling hands. "We might have found the missing piece of your theory." That accidental breakthrough, nicknamed the pigeon poop discovery, gave humanity its first glimpse of the newborn universe. Today, that historic horn antenna stands in a museum, still bearing dents from engineers pounding on it to fix the noise. This discovery earned Penzias and Wilson the 1978 Nobel Prize, and confirmed Lemaitre's theory just before his death. That microwave background radiation is the faint afterglow of the universe's birth. Everything we see, every planet, star, and galaxy, emerged from the Big Bang's expansion and evolution. But that also means the universe had a beginning, a creation moment, a time when yesterday didn't exist. For cosmologists, the next question was even more profound. Where did the universe come from? Chapter 2, The Known Future. Modern cosmology is undoubtedly one of the greatest achievements of contemporary science. It has successfully mapped the universe's evolution, from the first fractions of a second to billions of years later. Yet, surprisingly, cosmologists still cannot uncover the true origin of the universe. Despite having complex equations and precise observational tools, they remain unable to answer this most fundamental question. Behind this failure lies a blank space in our understanding of the cosmos. For over a century, a deeply awkward problem has remained unsolved in physics. Its source lies in the two foundational pillars of modern physics: which remain mutually incompatible, unable to even speak to one another. One of them is Einstein's general relativity, which explains gravity as the curvature of space-time. It is our foundation for understanding the large-scale universe. The other is quantum mechanics, which governs the subatomic world. It doesn't describe space-time curvature, but instead portrays reality through probabilities and wave functions. Each theory is incredibly successful in its own domain, yet mathematically they are completely incompatible. Their languages are as different as Chinese and French, utterly foreign to each other, unable to communicate directly. In most cases, physicists aren't bothered by this contradiction, because their work typically focuses either on cosmic scales or on the quantum realm, never both at once. But when trying to understand the very first moment of the universe, both theories must apply at the same time. In the universe's first instant, space-time was expanding rapidly, while particles and radiation, governed by quantum rules, interacted violently. In this chaotic era, all the fundamental forces had not yet separated. They were unified as one original cosmic superforce. Scientists believe that in the early chaotic universe, this superforce was neither gravity, nor electromagnetism, nor any of the known forces. It transcended both relativity and quantum mechanics, the master of all that would follow. It contained both of these fundamental theories. It was their source. As the universe expanded and cooled, this superforce eventually split into the four fundamental forces we know today: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Therefore, at the moment of cosmic birth, this unified superforce may have held the key to everything. Physicists began searching for an ultimate equation to describe this force, a theory of everything that could merge relativity and quantum mechanics into one. Over more than a century, countless theories were proposed, from extra dimensions, to supersymmetry, to string theory and loop quantum gravity. They were debated, developed, and many were eventually discarded or shelved, sinking into the dustbin of science. Despite endless efforts and failures, we still haven't found this so-called theory of everything. Without it, any speculation about the beginning of the universe is just empty talk, like a locked door we've never been able to open. Because this mathematical riddle remains unsolved, the truth behind that door is still unknown. We cannot describe what happened in the exact moment the universe was born. We cannot understand what occurred in that unimaginably brief instant. The true beginning of the universe remains a deeply buried secret. It seems as if the exploration has hit a wall. The story feels like it has reached an ending. We stand before this locked door, stuck, trapped by unsolvable equations. But if we could solve the riddle, if we could push open that door of ignorance, what lies beyond? Might we discover the ultimate origin of the universe? Might we even uncover the truth of what came before the universe itself? Now let us imagine. What might you see if you open that door? Chapter 3: A Universe from Nothing. Maybe Terry Pratchett was right. The author of the Discworld series imagined a peculiar universe, a flat world carried on the backs of 4 elephants, who stand on a giant turtle, drifting through the void. In that bizarre world, eccentric people brimmed with imagination. Some of them even pondered the origin of the universe. Their conclusion? In the beginning, there was nothing, then it exploded. Sounds absurd, doesn't it? Yet some physicists have proposed similar ideas. They believe that when we open the door to the beginning of the universe, what may be waiting for us is nothing. If you trace time back far enough, you reach a universe that's hotter and more lethal, until finally, you hit a limit, where temperature and density become infinite, and space and time collapse into an ultra-compressed state. Before that moment, there was nothing at all. But the nothing we're talking about here isn't just empty space. It's an absolute nothingness, no matter, no radiation, not even time or space. It's a kind of void we can hardly imagine, because everything we know, everything we can understand, relies on time and space. They are the backdrop, the coordinates for all existence. So if time hasn't begun, and space doesn't yet exist, what does nothing even mean, and how could the universe be born from it? If nothing exists, how do we even begin to talk about something? Physicists and philosophers often argue over this. What nothing means might sound like an empty debate, but depending on who you ask, the answer changes. That's why there's still ambiguity in defining nothing. And in that gray area, some scientists find a small opening. In the early 1970s, physicist Edward Tryon proposed a new way to solve the mystery of the universe's origin. His idea was rooted in quantum mechanics, the branch of physics that governs the probabilistic behavior of the microscopic world. Tryon suggested that the nothing before the universe was not a traditional vacuum, but a quantum void. In this state, space and time lose their clarity and certainty, because quantum effects cause everything to constantly fluctuate. Within this quantum vacuum, particles, radiation, even space and time could briefly appear and vanish. In a purely probabilistic dance, these fluctuations are frequent, but incredibly small, occurring only on subatomic scales. But here's the problem. When we look around, we see a universe full of energy. Kinetic energy, thermal energy, light energy, and mass. If the universe truly emerged from a quantum fluctuation, why didn't it vanish instantly? Why didn't it just cancel itself out? By all accounts, it should have disappeared in a flash. Tryon offered a bold explanation. We've been missing a key idea. The net energy of the universe is actually zero. It sounds hard to believe, but from the perspective of energy conservation, it makes sense. Yes, the universe contains lots of positive energy, motion, heat, light, and matter. But at the same time, there's negative energy in the form of gravitational potential energy. Gravitational potential is stored in how matter is arranged. For example, two masses separated in space attract each other and move closer. That movement comes from the potential energy they had to begin with. Unlike heat or motion, gravitational potential energy is negative, because separating masses takes extra energy input. So if you add up all the positive energy and subtract all the negative gravitational potential, Tryon argued they perfectly cancel each other out. The total energy of the universe is zero. That means, if a quantum fluctuation occurred with zero total energy, it wouldn't violate any quantum rules. The universe could appear from nothing and persist forever. But is this cosmic accounting actually valid? Is our universe really just a ripple that emerged from quantum nothingness? There's still no definitive answer. Philosophers argue that physicists haven't truly solved the problem. They've only shifted the question. Instead of asking where the universe came from, they're now asking, where did this quantum fog that birthed the universe come from? Physicists tend to ignore these philosophical concerns. They just keep building their theories forward. Many scientists are still trying to find the origin of the universe in the quantum realm, believing that our universe is a structure condensed out of quantum nothingness. Stephen Hawking once proposed that the universe exploded out of a region where time and space no longer had meaning, a realm governed purely by quantum probability and uncertainty. If the quantum origin model is correct, many questions still remain unanswered. One of the most intriguing, was the quantum fluctuation that gave birth to our universe a one-time event? Or is it happening all the time? In other words, are we alone, or are there other universes like ours? Maybe we're living in a multiverse, a vast ocean of quantum foam, constantly spawning new universes like bubbles. But the idea of a multiverse, we'll save for later. Right now, let's consider another unsettling question. Have we been here before? Does all of this feel strangely familiar? Chapter 4, Born in Fire, Dying in Fire. To borrow the words of poet Robert Frost, some say the world will end in fire, some say in ice. Our universe was indeed born in heat, but how will it end? In flames, or in frost? Today's observations almost all point to a single conclusion. The universe is expanding, and will continue to expand forever. As space expands, its temperature drops. It seems the universe is destined for a cold, silent extinction. But early cosmologists didn't think so. One possibility is that the expansion could stop and reverse into a collapse. If that happens, the universe would meet a fiery end, a collapse opposite to today's expansion, not cooling down, but heating up. At first, the heating would be slow, but as the collapse accelerates, temperatures would skyrocket, reaching millions, billions, even trillions of degrees. In this state, gravity and quantum forces would clash in a final showdown. In this seething sea of energy, quantum laws might prevent a complete collapse. Though heat and density would become extreme, they may never truly reach infinity. And if space-time never fully crumbles, then what comes next? One possibility is this. Just before the end, collapse halts, and the universe bounces back into a new round of expansion. This would mean rebirth in fire. Another Big Bang. A new universe is born. As it unfolds, atoms, stars, even life, maybe even us, might emerge once more. The new universe would expand again, only to collapse again, and be reborn in fire again. On and on, a never-ending cycle. The universe, born in flames, dying in flames, again and again. If that is the universe's fate, then its past may be just the same. Our current universe might be only a brief stop in an eternal cycle. Of course, some would raise a familiar question. If the universe truly repeats forever, where did the first cycle begin? Where was the starting point? To that, many cosmologists smile and point to an infinite past and future. After all, in the vastness of eternity, some questions can quietly vanish. But if the universe has existed forever, how could it just now produce something as orderly, complex, and alive as our world? In a universe that's infinitely old, why are we only showing up now? To address this puzzle, some have proposed a radical idea, that during cosmic collapse, the direction of time itself might reverse. In such a universe, chaos would reorganize into order. Entropy wouldn't increase, it would decrease. So when the universe is reborn, it starts fresh and young, a pure new world, untainted by the scars of the previous cycle. For most, this idea feels too extreme, not a satisfying answer for eternal cosmic cycles. But you needn't worry, because this isn't our universe's fate. We now know, the universe won't collapse. It will expand forever. Its ending won't be fire, but ice, a future of coldness and emptiness. Still, not all cosmologists agree. Paul Steinhardt proposed a very different model of the cosmos. He called it the cyclic universe. At its heart, a cosmos reborn again and again, in fire. In 2001, Steinhardt and his collaborators presented this model to the world, a universe that cycles endlessly, without fading. It's based on M-theory, a framework from string theory. In this model, the universe isn't just three-dimensional space. It's a brain, a membrane, floating in higher dimensions. In that higher realm, there are two vast, parallel brains. One of them is our universe. The other, a parallel universe. These brains periodically drift apart and then back together. Each time they collide, a new Big Bang is triggered. Each cosmic explosion is a result of two brains crashing together in a higher dimensional space. After the collision, the brain's internal universes expand and cool, forming galaxies and life. Over time, the universe grows old and thin. But in the higher dimensions, the two brains are slowly drawn together, until they collide again, and a new bang begins. A cycle without end. What about entropy and decay? Supporters of the cyclic universe believe that extreme expansion dilutes and erases all past disorder. Each new universe is pure and untainted, carrying no memory of the one before. Of course, this theory is far from universally accepted. Though it presents a complete picture of eternal rebirth, it fails to answer one critical question: where did this endless cycle come from? And more importantly, why must this model rely on just two colliding brains? What if our universe is just a small part of something far bigger? To many, the ultimate origin of the cosmos lies beyond this universe, hidden within the higher realm of the multiverse. Chapter 5: A Journey Through the Multiverse. Robert Dicke was one of the most insightful scientists of the 20th century. He was the one who received the phone call from Penzias and Wilson, and immediately recognized the significance of their discovery. At Princeton University at the time, Dicke was leading a research team attempting to measure the cosmic microwave background radiation. If not for that serendipitous signal, Dicke himself might have stood on the Nobel stage. Dicke constantly contemplated the nature of the universe, especially the unusual ideas of physicist Paul Dirac. Dirac, a pioneer of quantum mechanics, won the Nobel Prize in 1933. He also noted a startling coincidence. Certain fundamental constants of nature, like the speed of light and gravitational strength, when combined, yielded a value close to the age of the universe. It was perplexing, because physical constants are fixed, while the universe's age is always changing. Why, then, would two seemingly unrelated numbers coincide so closely? Either it was an extreme coincidence, or physical constants themselves might vary over time. Dirac proposed that those constants we consider eternal, might actually change as the universe evolves. The idea was initially dismissed as mathematical happenstance, but Dick believed the coincidence was not accidental, that it reflected a deeper truth, a secret capable of shaking our cosmic worldview. Early in its history, the universe lacked the conditions for life. Heavy elements like carbon had yet to form through stellar nucleosynthesis. Life depends on these elements. Their generation and distribution takes time. Exactly the time scale suggested by those coincidental constants. Thus, those numbers weren't coincidences, they were prerequisites for life. Our existence in this epoch is no accident. It's because life could only emerge now. In other words, this isn't just a random moment, it's a selected time window. Dick pointed out this as a selection effect, challenging the Copernican principle, the idea that humans are not privileged observers in the universe. But Dick argued that the existence of observers places constraints on cosmic conditions. Only in a universe that supports life can observers appear to study it. This problem led to the concept of the anthropic principle, considering factors necessary for life, like carbon formation in stable stars. Our location in time and space is not random, but necessary for our existence. Some extended this logic into the realm of physical laws. Remember those fundamental constants? They determine the strengths of forces, particle masses, and more. Current theories cannot explain why they have the values they do. We can imagine universes where these constants differ. One universe might have electrons 100 times heavier, another with no gravity, or electromagnetism too strong. Most such universes would be barren, sterile, lifeless. By contrast, our universe seems just right. Laws of physics seemingly fine-tuned to allow galaxies, stars, planets, and life. This precision tuning is the core of the anthropic discussion. For some, it's meaningless. We can only exist in a universe capable of supporting us. Others argue this perspective is evasive. If we accept our existence without asking why, it feels unsatisfactory. Viewed from a broader standpoint, Dick's anthropic principle suggests our universe may be just one among a vast multiverse. We live in one of many universes, each with different physical laws and constants. Some may be incompatible with life. We exist in precisely the one that is. This raises a deeper question. Who, or what, is doing the selection? Are all those hypothetical universes real? If so, how many are there? Mention the phrase multiverse at any physics conference, and the room immediately divides. Some call it unscientific. Others counter that, dismissing it as narrow-minded. To understand why, we need to clarify what the multiverse is and isn't. It's not a single physical theory. It's a broad scientific hypothesis developed to account for fine-tuning issues. It's not one theory but a collection of related ideas spanning multiple versions and branches. How does the multiverse explain cosmic fine-tuning? The story links to the century's greatest dream, a theory of everything. As we discussed earlier, physicists hoped string theory might unify all laws. At the tail end of the 20th century, this hope centered on M-theory, an extension of string theory. Originally, researchers expected one outcome. Their calculations would yield our universe's exact physical laws. Instead, they found something astonishing: countless mathematically consistent universes, each with its own set of constants and forces. These alternate universes form the so-called string landscape. Some universes have stronger gravity, weaker electromagnetism, or entirely new forces. Virtually any combination possible. As the fine-tuning problem highlights, most of these universes would be lifeless and structural voids. Our universe is simply one rare exception. In this context, the multiverse provides a coherent answer. Our universe exists because, in the sea of possibilities, one had to support life, and we happen to be in it. Each universe in the multiverse randomly draws its laws at birth, like pulling a configuration card from chaos. How many universes must there be before one emerges with conditions suitable for life? Conservatively, estimates start from 10 to the power of 500. Some argue there are literally infinite universes. In that vast landscape, most universes are lifeless, empty, cold, but one or a few support life, like ours. This is an extreme form of the anthropic principle. We exist here because we must exist in an appropriate universe. Otherwise, we wouldn't be here to ask. However, this hypothesis comes with heavy implications. It implies an unimaginably vast structure made up of countless dead universes. That leads to new questions. How are these universes created? Are they each born from quantum fluctuations? Or does the multiverse simply extend infinitely into the past and future? Some suggest the multiverse is a natural consequence of cosmic inflation theory. Most cosmologists believe inflation occurred at 10 to the power of minus 33 seconds, a burst scaling the universe by times 10 to the power of 40 in an imperceptible instant. This process smooths out irregularities and solves key cosmological puzzles. Because of this, most believe inflation happened. Theories propose a strange field, the inflaton, drove this explosion. What triggered it, and what ended it, remains unknown. To explain this, some researchers proposed eternal inflation, the idea that inflation never truly ends. In eternal inflation, some regions stop inflating and condense into bubble universes, while inflation keeps going elsewhere. Perhaps our universe is one such bubble, formed when inflation ceased and energy transformed into matter and radiation. Each bubble universe anchors its own physics, laws and constants frozen in its birth moment. These bubble universes are unimaginably large, far exceeding our observable cosmos, and they continue forming across a turbulent eternal inflating background. Each bubble may differ physically from its neighbors. In the eternal inflation plus bubble universe model, inflation acts like a cosmic engine, generating infinite universes. We live in one randomly selected bubble among countless others. For some, the multiverse theory feels not only reasonable but beautiful. It elegantly addresses the fine-tuning problem without invoking miracle or design. Yet critics argue, it may lie outside the realm of empirical science. Infinitely many universes we can never observe. If we can never detect them, can this concept still qualify as science? That question lies at the heart of academic debate. Some say the multiverse is a natural extension of cosmic logic. Others counter, once we accept it, the question why these laws loses meaning, because all possibilities simply exist. But remember, multiverse theory remains an unproven hypothesis, a theoretical framework under active exploration. Only if we find ways to compute it, test it, and validate it will it become fully scientific. Perhaps one day we will decipher its mathematical foundations and bring it into empirical science. Or perhaps one day we'll observe subtle evidence of other universes indirectly. Even if the multiverse is real, some find it philosophically troubling. The sheer waste implied. Countless lifeless universes just to allow a few rare life-permitting worlds. Maybe the universe need not be so wasteful. Perhaps we can borrow ideas from biological evolution to rethink cosmic evolution. Chapter 6, A Darwinian Cosmos. Alfred Russel Wallace. A name that should be far more celebrated in the history of science. In the early 19th century, Wallace left behind a career in civil engineering and set out on a journey of exploration. He ventured deep into the Amazon wilderness and across the Malay archipelago, conducting field studies. Along the way, an unusual idea about the diversity of life began to take shape in his mind. By observing birds, monkeys, and many other wild species, Wallace realized that natural barriers, like mountain ranges or rice paddies, can isolate populations. Once isolated, these groups adapt to their unique environments. Over vast spans of time, they may eventually evolve into entirely new species. Wallace documented his observations in a series of papers. By the mid-19th century, his findings found their way to another naturalist, Charles Darwin. Darwin was already known for proposing the principle of natural selection, survival of the fittest, evolution driven by environmental adaptation, culminating in the emergence of new species. The diverse finches of the Galapagos Islands became iconic examples supporting his theory. Yet Darwin had not publicly shared his ideas, choosing instead to refine them over many years, crafting a thorough argument for the evolution of life. When he encountered Wallace's paper, he realized the urgency. His own theory was about to be preempted. Darwin swiftly organized his thoughts, wrote a paper, and soon released On the Origin of Species. He secured his place as the father of evolutionary theory and the foundational architect of natural selection. He never dismissed Wallace's role, and they frequently exchanged letters, co-submitting their paper to the Linnean Society of London. After Wallace returned to England in 1862, he became a strong advocate of Darwin's theory, vigorously promoting it worldwide. Fast forward to the early 1990s, Physicist Smolin posed a thought-provoking question. Could the universe itself follow a process akin to natural selection? Is there a mechanism that favors universes capable of supporting life? What would such a fitness criterion look like on a cosmic scale? Smolin suggested the answer might lie within the universe's most mysterious phenomena, black holes. These arise when supermassive stars collapse and expire. At that moment, space-time is warped to its extreme, potentially reaching a state of infinity. Could new space and time be created within such extremes? Might an entire new universe be born inside a black hole? In our observable universe, about 50 million stars undergo supernova explosions each day. If Smolin's idea is correct, millions of new universes are born daily from those dying stars, akin to newborns entering the cosmos. These baby universes are not perfect copies of their parent. Their physical constants vary slightly, much like genetic mutations on Earth. If those offspring universes can form stars and black holes, they can propagate further offspring, creating generations of universes. Thus emerges a cosmic lineage, universes giving birth to universes. But universes unable to form stars or black holes cannot reproduce, just as extinct species fail to pass on their genes. Only universes capable of building stars and black holes can thrive, becoming members of a multiverse rich in galaxies, and possibly life. How then does life silently appear within this cosmic selection? Keep in mind, only universes that can produce stars can forge heavy elements like carbon, oxygen, iron, and sulfur, which are essential for life. Thus in Smolin's cosmological model, life isn't an anomaly, it's an expected outcome. That said, Smolin's theory, while compelling, does not solve the ultimate question. What sparked the very first universe? If our universe is a victorious survivor among many evolutionary dead ends, what was the original trigger? Maybe cosmic natural selection adds more complexity to an already deep mystery. We're nearing the end of this journey, but more questions remain than answers. The origin of the universe is just as enigmatic today as 100 years ago. Theories like the multiverse and quantum emergence continue to theorize the first seconds of existence. The search for a theory of everything is ongoing. Physicists are pushing against the limits of M-theory, exploring new models, new ideas. If one day they break through that towering math barrier, secrets hidden for billions of years may finally be revealed. Perhaps they'll confirm theories like quantum vacuum or multiverse, or verify the Big Bang occurred 13.8 billion years ago, or discover there was no origin at all, or something more elegant beyond current imagination. But till then, look at the beauty of our blue planet beneath your feet. Our world is precious. Even seemingly mundane moments, early mornings, sunsets, the shifting stars, dancing leaves, drifting clouds, chronicle unique beauty. Because in space, there's no sound, no trees, no meals, no loved ones, no books, no music, no pets. Don't take these things for granted. Each of us holds the ability to deeply connect with the world around us. That's why we look up at the stars, asking timeless questions. What lies beyond? Is there anywhere else like our home? Maybe we live on a small cosmic paradise. As astronaut Jim Lovell said, people often say they hope to go to heaven when they die. But if you think about it, haven't we already arrived the moment we were born? Thank you for watching this episode. If you enjoyed it, please like, subscribe, and share. See you in the next episode.